Yeah, go, yeah.
Okay, good morning, everyone. Welcome to the Vaughan lecture series. Today's lecture would be given by our colleague, Professor Vaughan Voller. Vaughan has been at the department for a very long time. He got his education in England, and after completing his PhD in applied mathematics, he came to the department. At that time, it had a different name, as a postdoc. Then Vaughan got back to England, where he was a senior lecturer at University of Greenwich, London. And eventually he came back, and he started as an assistant professor and made all the way to the full professor, which he became in '97. Vaughan has an outstanding publication record. He authored, I don't know, probably close to 150 papers. His citation index is out of roof. He's one of the strongest in the department. Vaughan's interests are in modeling and analysis of geosystems. They're quite versatile. So also development of computational methodologies for analysis of thermal fluid system, modeling of solidification of alloys, development numerical techniques for free and moving boundaries, simulation tools for analysis of polymer mold filling, thermal stress, cracking, etc. So he has a number of honors and awards, but I don't want to take much time, and please join me in welcoming Vaughan.
Thanks, Bobby. If nothing else, it's convinced me I should shorten my CV on the web. So I'm going to talk today about anomalous diffusion. I'm going to try and look at stochastic, physical, and numerical models. First of all, the main thing I'm really going to be after is trying to explain what I mean by anomalous diffusion. And this is work that I've been working, an area I've been interested in for about 4 or 5 years. And I've been collaborating closely with Professor Hill in the department, Pietra Rebecca, who's a mathematician at the University of Warsaw, and a former postdoc of mine, Fede Fallicini, who I think that's CNR Rome. I'm not quite sure, but it's the National Resource Organization. I think I got that correct. So what I'm going to try and do is 3 things. I want to actually try and explain in a very simple way as I possibly can by an example. I realize I'm an experimentalist at heart. I mean, I do mathematics and numerics, but most of what I do, even with the numerics, is experiments. I want to show a very simple stochastic experiment that will demonstrate what anomalous diffusion is, something that you could actually do yourself quite easily. And then I'm really interested in, well, if you see this thing, anomalous diffusion, how could it actually be realized in engineering systems? And I want to show a very simple experiment, a very simple system related to infiltration, where you see a clear, unambiguous signal of anomalous diffusion. And then I want to talk a little bit about, if there's time, Sonia tells me the clock runs out at 11 o'clock, to talk about how some ways in which you might model anomalous diffusion, and that comes into another interest of mine, which is fractional calculus and fractional partial differential equations. So I want to start off by looking at just the basic stochastic model of diffusion, which maybe goes back to Fick, and certainly was more characterized by Einstein in 1906. So I want to imagine a very simple experiment that you could operate on the computer. It's easy to program in MATLAB, and involves a simple one-dimensional random walk, where you have a particle that starts at the origin, and it can move 1 step to the right and 1 step to the left. So you say you're going to have a 20-step simulation. So the particle goes 1 step this way, 1 step this way, 1 step back this way. So it just steps backwards and forwards. And at the end of 20 steps, on average, it should be back at the origin, but of course, there are going to be times when it's going to be removed and remote from the origin. And what you do is you do this experiment 2,000, 5,000 times. So you start a particle off at the origin, and you say, I'm going to let you walk for 20 steps, left, right, -1, +1. You do that 20,000 times, and of course, the result is that you'll end up, after 20,000 realizations that I've tried to show the ending points here, that you'll end up with a distribution of ending points of where that walk will end. The mean would be 0 if things are done correctly. Your random number generator was correct in the computer, but you'd have a spread that would happen in that case. And you could measure an average location by doing a simple root mean square, which would be like the standard deviation of that spread. And then I can repeat the process, but now rather than taking 20 steps, I can take 40 steps. And that would be like a proxy for time. So I just now take 20 steps. Here I'm taking 40 steps, so I'm going to see more spreading. And I can think of the 20 steps as being a time step, and 40 steps as being, so 20 steps is time step 1, 40 steps is 2 time steps. And then I can repeat the process again. And you can see what will happen is that this root mean square, the standard deviation of the ending points of those 25,000 realizations will spread out with time. And if I was to repeat this, maybe do 10 versions of it, and I was to plot how this spreading, the length scale of that spreading changed, the standard deviation, if you will, of that spreading change with time, I would see this classic diffusion signature. I would see that the spreading, the thickness x, would go as the square root of time. Well, not quite as 0.508 in this simulation, but for me that's reasonably close. So I get the idea that this kind of simple Brownian motion, as it's called, just moving left and right with steps of 1 will give me this 0.5, which to me as a characteristic time scale is the time scale of diffusion. And that's kind of been known since Fick in 1855, and it was characterized more fully by Einstein. I mean, what Einstein did, in fact, was that he looked at this probability distribution, W, which is the probability of a particle being at location X at time T. And he was able then to write down what's known as the master equation and show that you could look at this probability density function of this spreading, this probability density function could be written as something that looks to me very much like a diffusion equation, where W is this probability density function of the probability of a particle being at location X at time T. And of course, we know then that that's related, closely related then to a diffusion type equation. And we know that if I was to take a concentrated pulse in some field, some concentrated material, a chemical, for example, in a field that had no flow, that it would spread out with time. And to spread out over time, would have a kind of Gaussian distribution shape. And I just can describe how that concentration spreads with time by taking this diffusion equation, which is directly related then back to the Brownian motion PDF of this location function. And so then this is the classic diffusion transport equation. The original version of this equation, I think most of the original versions were phenomenological. I think Fick probably wasn't phenomenological, but Fourier certainly was. That was based on observation. 1822 was when he published his book on the theory of the transport of heat. Fick did this case for chemistry. And then to some extent you could argue that Darcy also has a diffusion type law, and that was purely phenomenological. And the idea is that you would see that this spread, this characteristic length scale associated with the diffusion process has this square root of time dependence. So it spreads with the square root of time. And so that's normal diffusion, having this characteristic signature of the square root of time. But now let's look at what would happen if okay, this is an important comment, Steve. Randall's probably going to pull me up about this. So the interesting thing is, of course, as mentioned, that spreading takes a normal distribution. It spreads with a normal distribution, but it was made up by choosing steps from a distribution of just +1 or -1. So I didn't even start with a normal distribution, but how did I end up with something that was normally distributed? I ended up with something that was normally distributed that has this classic spreading square root of time behavior because of the central limit theorem. So if you choose, and in fact, any random walk or any Brownian motion I do, as long as I choose the step sizes from PDFs that are what's the word I've used? Are suitable for proving the CLT, then the central limit theorem, then I'll end up with this square root of time spreading. So it doesn't matter how I choose the steps, as long as the distribution is compliant, is that the right word, or wasn't it? With the central limit theorem. And what that means is that that distribution has a finite mean and a finite standard deviation. And some distributions don't. If they don't have that, then they don't agree with the central limit theorem. And so we can see what the consequence of that might be let's say we want to look at modifying our Brownian motion so that we now include steps that chosen from a PDF. We modify or arrange our step sizes from the PDF so that they won't agree with the central limit theorem. And the way we can do that is something called a continuous time random walk. So it's almost identical to the previous walk that we did, the Brownian motion. We're still going to move in space one step to the left or one step to the right. Still going to be chosen at random as +1 and -1. The difference is that between each of the steps, we're going to wait for a certain period of time. And so this is going to add to the clock time. We can imagine before that each step represented some amount of clock time, but now we're going to add to the clock time and wait in between taking each step for some period of time. And a randomly chosen period of time, a clock time. And then you can see what will happen is, of course, that if you remember from the previous slide, that for the same amount of steps, it will slow down the distribution. So one thing it will do is slow down the spread. And if I was to choose the step sizes from a Pareto power law distribution of this form, so I choose the waiting time, so the waiting times between the steps from this power law distribution, and I choose it such that I can find, this is a distribution that if alpha is less than 1, will not have a standard deviation or a mean. So it doesn't agree with the central limit theorem. And so I'm just waiting for this power law step. And you can see that what it means is, because it has this power law tail, that sometimes I might be waiting for a hell of a long time before I move. So some of those examples, some of those realizations, the thing will sit still for almost forever before it moves again. And when I add this, I get a similar spreading, well, not similar spreading behavior because it's kind of much smaller. The spreading is not as fast, but not only is it not as fast, it doesn't agree with the square root of time anymore. So I lose that square root of time dependence. As soon as I make this alpha, as soon as this alpha becomes greater than 1, I go back to the square root of time, go back to the square root of dependence. But between alpha of 1 and 0, I actually see that I end up with an alpha upon this exponent on time is the alpha value divided by 2. If alpha is greater than 1, I go back to a half, regardless of how much greater than 1 is. If less than 1, I start seeing this, what people call sub-diffusive behavior, anomalous diffusion behavior. So this is the idea about what anomalous diffusion is, in this case where we have diffusion that the spreading is slower, but that's not the key. The key is that the actual length scale of the diffusion process is not scaling with time t to the half, but it's time t to something less than 1/2. It could be greater than 1/2 too, but in this particular case, with the waiting times, we're getting this sub-diffusive behavior. So here's a very simple experiment that you can, it's 4 or 5, maybe 10 lines of MATLAB code, 3 lines of Python code, Chris, I'm certain, that you could do this example. And I just wanted to do it to convince myself you can do this mathematically, as I'll show in a minute, that this would actually work. And what you can do mathematically with this, so I'm just trying to indicate this alpha upon 2. Well, you can do alpha, you can do the same kind of thing that was done by Einstein, and you can develop this master equation. I've never got quite on top of the math of how to do that. It's nicely explained in this great paper by Metzler and Klaffler. You can actually then take this Fokker-Planck equation I wrote down before that Einstein developed, but you now write it down as a fractional Fokker-Planck equation, so that the time derivative of the PDF is a fractional derivative where alpha is less than between 0 and 1. So that's how I can bring this fractional derivative. So that's a nice connection between this continuous time random walk and being able to write down a fractional diffusion equation and this anomalous diffusion. And again, then we can relate that to a diffusion process that now has this form. This is a kind of one that we would want to use as a transport equation. So we now have alpha in here, which is less than between 0 and 1. Strictly greater than 1, less than or equal to, strictly greater than 0, less than or equal to 1. And so it's a nice way of being able to motivate why you might have a fractional calculus equation that comes in there. What do I mean by fractional calculus? So this is a fractional time derivative, and what does that look like? Essentially, you don't want to get too turned up with thinking that it's anything to do with calculus. It has something to do with calculus. But it's basically a convolution integral is the way you would define it. Becomes defined through this convolution integral in time. And the way to think about it is it introduces a memory into the system. So it's essentially introducing a memory by having this. Have I made a mistake, Randall?
What's capital T?
Oh, should be C.
Okay.
Thanks. I'm rehearsing this talk. I'm going to give it next week, so it's great that you pointed that out. Yeah. So it's basically a weighted sum of all of the concentrations back through time. So that's what I'm saying is a memory. That's a serious mistake. Yeah.
Just to check, the alpha is the same alpha as in the last slide.
The alpha is the same. This alpha, yeah. The alpha would, I mean, yeah. The exponent in the two. Yeah, yeah. You could think of it in that way, but yeah, it is. It is the same alpha. It would be exactly the same alpha. And it would be the exponent of the tail in the power law. So what I'm interested in then is this equation and the idea of anomalous diffusion, saying, well, that's great. You've done this little thing with this particle moving around. What does that? When can I actually see that in a kind of engineering or natural system? And one place we see it all the time is, of course, in flow and porous media, but I want to try and be a little bit more general than that. And the kind of general consensus is, and again, this is, when you read the literature, that every paper that starts off with this says this statement that if you're going to have heterogeneities in your system, in your transport system, and the heterogeneities vary across a wide range of length scales, up to and including the system size itself, then you might see this sub-diffusion occurring. So one of the idea is that if your system is set up so that it has hold-ups to the transport, and you have this kind of distribution of length scales I've tried to illustrate here, so you can see this thing trying to diffuse or move through this system and having to move around the obstacles, then in those cases you see this sub-diffusive behavior coming out from those systems. Counter to that, if I have a system where you have fast paths, so I still have heterogeneities, but now the heterogeneities are not preventing this transport process, they're actually enhancing the transport process in some way. So you can imagine you have wider channels, which I've tried to indicate here. Then you still get a fractional diffusion equation, but it's fractional in the gradient term, not in the time term. And this actually leads to super-diffusive behavior where the spreading will go as greater than half. And I can also demonstrate that with that simple stochastic model. But I'm actually going to focus more on this case. So that's the kind of consensus, but I'd still like to try and get some teeth to that and actually see what it really looks like. And this is a nice thing from Greg Tucker at the University of Colorado Boulder to try and describe these two competing processes. You could kill both of them. In the US, they call it chutes and ladders. In Europe, we call it snakes and ladders. But the idea is that you're transporting through the system, and sometimes you get a fast path, which is a ladder, and sometimes you get a hold-up, which is a snake. It's a very nice way of describing the system. And that's as I say, I think Greg was the person I heard that from first. So you often see this in porous media flows. We know that in groundwater we have a very wide range of heterogeneity of the soil types. It spreads across many length scales. But I want to try and see if we can see that in a more kind of tangible sense. And people have done experiments. So the thing I'm interested in, and it's actually not 40 years, it's 39 years. I think it's almost 39 years ago that I started my PhD. Almost exactly to the day, I'd say. And the first problem my advisor said, well, I want you to look at the Stefan problem, which is melting ice. And I realized that ever since that day, no matter what area I work in, and Sonia raged a whole pile of different things, I always just come back to this problem. I always say, well, how does that apply to the Stefan problem? So the first time I heard about fractional calculus and anomalous diffusion, I said, well, how does that apply to the Stefan problem? So I want to investigate or look at that. And of course, it's not just any Stefan problem. It's the 1D Stefan problem. It's the only one worth doing. So that's another case of melting ice, which is more interesting. But so here's a 1D Stefan problem. So I want to actually look at this system, this simple melting system, and try and see if I can find an anomalous diffusion signal in there. What would it look like? What would it take to have a melting system that would demonstrate anomalous diffusion? So this is a one-dimensional problem. Initially, I have a block of ice, which is at the phase change temperature of 0. I raise the temperature at this side to 1 and initiate the melting. And then this melt front over, if I keep this at 1, this melt front over time will move forward in time. Inside the melt region, I can describe the temperature profile by the standard Fourier second law of heat conduction. At the front, the temperature is equal to 0 at the front, but I also have this Stefan condition that says the velocity of the front, ds by dt, the position of the front, is driven by the thermal gradient coming into the front. In order to, and I've assumed here the latent heat is 1, so I've got to dissipate the latent heat by applying the gradient, and this moves the front forward. So that's the problem I'm interested in, trying to look for signals in anomalous diffusion. Can I create anomalous diffusion in that case? And of course, I could solve this problem, the classic Neumann solution. It turns out that this movement of this front will be at the square root of time. So that gives me a kind of hook to which I can start to think about anomalous diffusion, because if I could create an anomalous diffusion phase change problem, I would expect that this front wouldn't move with the square root of time, because this is a direct consequence of the similarity in the problem with the fact that you have the diffusion, that it's a diffusion problem. And in fact, we do, in phase change systems, you do actually see what could be termed as sub-diffusive behavior. So here's an example of building up ice, an ice layer, frost layer in a fridge. So it's a kind of phase change problem. You're building this ice layer. And then that thing about when you build the ice layer, when you look at it, there really is a lot of heterogeneity in terms of how the ice crystals lay and where the air is. And when you plot the growth of the ice layer, it doesn't follow a time to the half. It follows this it can follow a sub-diffusion case, and to make life very confusing, it can also follow, in some examples, have shown that it's actually super-diffusion. So this could be experimental error, but it's a system where people have actually seen deviation from the square root of time behavior in a phase change system. And again, this is probably just, when you look closely at the ice, you can see how you might have some fast paths that are running through the entire system, or you might have this kind of places where heat transfer could be slowed. So I don't really want to look, I want to look at the Stefan problem, but I want to look at a particular version of the Stefan problem. And this, I think this should be familiar to many people in the soil mechanics thing. This is a simple Darcy experiment, but this is actually a very simple Stefan problem. So I have this classic Darcy apparatus. It's empty to start with. There's atmospheric conditions down in the porous medium. I'm going to hold a fixed head on the left-hand side. So the fixed head on the left-hand side is then going to drive this infiltration of fluid into the system. And here, the system looks almost the same. So the speed of the front is again controlled by the head gradient. So the rate at which I can supply moisture to the front determines how fast the front moves. But in the body, in the stuff that's already infiltrated, I have a much simpler equation, because essentially I don't have any specific heat. There's no kind of lock to the path, so I can just write down my diffusion equation is basically there's no transient term. So just because it's a very simple system, this is going to make life a little bit easier for me to deal with. And it turns out, of course, that we could also think about this problem as a version of the porous problem, as the idea of a Healy-Shaw cell. So if I have two plates that are very closely spaced, and I'll try to lay them out here, and I put a pressure gradient, a uniform pressure gradient or head gradient across this side here, then it will drive a flow into the plate, in between the two plates. So then they're close enough together, that's a potential flow like Darcy flow. So it's like it mimics the Darcy flow of the porous media system. So I've gone through at least two iterations. I've gone from the Stefan problem to the Darcy problem and now to this Healy-Shaw problem. The equation in the Healy-Shaw problem, assuming this front is going to be one-dimensional, is the same. Inside this filled region, I have a very simple potential equation to solve. At the front, it's going to go as the square root of time, and at the front, I have this condition on the head gradient. And of course, before anyone gets too excited, I'm going to be using, yeah.
Sorry, but just to make sure, you said what the condition that you impose is a constant pressure gradient.
Yeah, constant pressure head. Yeah. Along that surface there, sorry, HEP.
Pressure on the left edge.
Yeah, sorry, yeah, thanks, Chris. I always often use, when I get nervous, I use the wrong words all the time. So we're using glycerol, which is the correct name for glycerine, And it's about 100,000, so the viscosity is 100,000 times larger, I should say, than air. So there's going to be no fingering in this system. Before people start getting worried about the fingering point, it's going to be eliminated. I'm glad did Bill get, he's still here, yeah, good. That's the chemical. I decided to have at least one of these in the talk to make it viable. Now we've got the word environmental in our title, so I've added that. So and I don't expect you to follow this, but this is a very straightforward solution just to show to you that the front will actually move as the square root of time. I can solve this equation. The boundary conditions then are a constant head at x equals 0, 0 head at the front. This simple equation, I can solve that simple a linear solution for the head. I can put this linear solution for the head into the equation for the speed of the front and end up with this equation for the front speed that has the solution of square root of time times square root of 2 times square root of t. So that's a very simple differential equation that you can solve just to convince you that I do see this signature. So now what I want to try and do is, can I disrupt this problem so I don't see this signature square root of time coming up? That's what we're trying to do. So, but before I do that, I can also solve this numerically. And I use what's known as a diffuse interface method to solve this numerically. Some people know what I mean by that. So effectively what I do is, rather than assuming there's a sharp front, I'm going to assume that there's a relationship between this liquid fraction, which is either 1 or 0, and the pressure head. And it changes smoothly from 1 inside the fill region to 0 outside the filled region. And I'm able to take this set of equations and write it down as a single equation, where I just track the evolution of the front through this liquid fraction F, which if I integrate will give me S, which I'm going to also call the infiltration factor, capital F. And so that's a way in which I can track the front using this numerics. The nice thing about this approach is it allows me to use a fixed grid to solve it on, so I don't have to track the front. And the solution is pretty spectacular. I have to say, it comes out almost perfect. I don't know, and this is a fairly coarse grid. So this F factor, which is the same as F, square root of 2, almost, not quite, 0.5, almost, not quite. Fit is about R squared equals 1. So I can solve it numerically. And hopefully, if I don't run into the geomechanics seminar, I'm going to come back to this slide because it has an important consequence at the end when I start messing around and putting fractional calculus things in here. So what I want to do is to go back to that problem and see then, so can I disrupt this square root of time behavior? And what I'm particularly interested to do, if I was to introduce obstacles into the cell, flow obstacles into the cell, could I arrange them in such a way that I would see an exponent coming out from here which wasn't 1/2, but it was less than 1/2? And I thought Kimberly was going to come. Oh, she's here. Yeah. So this is work that I was fortunate enough to be able to connect with Kimberly's group, and we decided to actually do some experiments. So these are not, I did numerical experiments first. So I knew the experiments are going to work, but I decided I wanted to report on these physical experiments. So what we're going to do is we're going to do this infiltration experiment, keeping ahead, forcing the flow into a Healy Shore cell, but we're going to try and disrupt that flow by putting in flow obstacles. So we went and did some 3D printing, and we made this base, this blank, if you will, which is about 100 millimeters by 100 millimeters, and it allows for about a 2 millimeter gap for the flow to get through. But in the direction, so the flow is going to be going this way through the system, but we have these raised obstacles. And then we put a perspex plate on top. So those obstacles go all the way through the thickness. So the flow has to go around the obstacles as we push them in. And here you can see I have one that has a fairly simple pattern. And this is then what it would look like. So if I'm pushing here, I'd have a tank that keeps a fixed head. It forces the flow, which is the red, into the system, and it moves around the obstacles. This is, so these are air spaces, even though this is the grid that I got from the thing. And then this you can think about as being the face front. But what I want to track, though, is the variable I'm going to track is this infiltration factor, which is the area of the fill space divided by the width of the plate. And so if I had no obstacles in there, that would be the position of the front. But if I put obstacles in there, it's exactly the same as infiltration would be in the typical hydrological sense. It's the length, equivalent length of fluid I'd have to put in that's been pushed into the system. So I just want to, so this is the variable I'm going to track. I'm going to track how F changes with time. And this is the apparatus that Kimberly and I developed. So we're going to have this tank. We're going to have about 20 centimeters of glycerin. It's being dyed black so we can see it more easily. And then we build this plate and push it up against the tank, and we have a gate that we flip open. This is much, much more fluid than can be held inside the cell, so we can assume we keep a constant head as it moves through, and then we simply use, I don't use that simple, appropriate lighting, high-speed cameras. We film the motion, incoming motion from the top. This is what it looks like. This is, you can see maybe where I'm going with this. So this is a particular pattern blank that we did. Has some kind of fractal dimension, which I'll talk about later on. This is what the flow looks like. This is a very poor man's video. I just got it done. You can see that we do get some kind of air bubbles forming, but in general, we're having a fairly nice progression of the fluid into the front. When we compare it with numerical simulations, we've taking the, maybe adjusting the viscosity of the glycerin, which can be very variable to some degree, but we get very good comparison both in shape and time. So the right is showing numerical simulations, direct simulations, and the left is showing the equivalent time in the experiment. So there seems to be good compliance between the experiment and the simulation. So the idea then is to, so we know that if we have no obstacles, that my infiltration should go as the square root of time. I just tried to demonstrate that if it ties up with the theory. So I know that should be the case. But now I'm interested in cases where that might not be true. And because we had this idea of length scales, heterogeneous length scales distributed over a very large range of length scales, power law distributed perhaps, the place to go is to go to fractals. So we're going to use the classic Sierpinski carpet. And of course you could argue this is not a fractal. This is not a fractal. It's just it's not going infinitely because obviously I can't print infinitely. In fact, printing and even doing the simulations down to this third order is quite difficult. But the one thing that characterizes these shapes, these patterns then, so the black bits represent where the obstacles are going to be that I'm going to have to push around. The thing that characterizes it, that there is no, what I would say, there's no internal length scale. There's no pattern, in other words. I can't find a subscale or in any of these three carpets, which when repeated would give me the whole carpet. Right? So there's no internal length scale to any of that. The length scale of that pattern is the size of the obstacle itself. And so by contrast, if I looked at this pattern, then we can see that this has an internal length scale of 1/4. So this pattern in here just repeats 4 times, 4 times this way, 4 times that way. So that's going to be the important distinguishing characteristic that we need to be interested in. Because then, so if I do the base cases, and the second base case is probably the most important one. So the first base case is just confirming that we get good compliance between the experiment and theory. And I think the black line actually is the theoretical line that we would get. And we can see this is log-log plots. So I'm looking at log f versus time. So now I don't get that nice parallel curve and getting a straight line. And the gradient of the line will be the exponent that I'm after. So you can see when there's no obstacles, 4.493. So within some kind of experimental error, I would say that's quite reasonable. What's kind of more interesting is that when I put internal length scales in, but they now have this pattern, so I still put obstacles in there, I still recover something which I could say has the signature of diffusion. So you can see we did 2 experiments in this case, and we got values spanning on either side of 0.5. So having obstacles in there alone is not sufficient to give me anomalous diffusion. I'm still going to see the same diffusion signature being persistent through the case. But when I look at, and I'm summarizing quite a lot on this slide, when I start to look at these fractal obstacles, I start to see clearly see a very strong deviation from it. So the first one is the n equals, I'm calling it n equals 3. You just count the kind of squares, 1, 2, 3. And there I see now 0.423. So I say that's actually quite significant, and I think statistically I could show it. So that's significantly different from 0.5. I've got a 0.423. If I make the pattern even more incongruent, so this is an n equals 4, that number reduces. So it goes from 0.423 to somewhere around about 0.35. The other thing that's fairly interesting is, and in the simulations it's almost exact, here there's some range of variability at this particular n equals 4 carpet, but in the simulation the number comes out to almost be exactly the same, and they're reasonably close, again within statistical bounds. This power law, the n t to the power 0.36, is very consistent for a carpet of a particular design. And the other thing that's important is, it doesn't, so what I'm saying is it doesn't really make too much difference if I make it a really complicated pattern, fractal, versus a very simple one. What's key is that there's no internal length scale, and somehow all these patterns have the same fractal dimension, by the way, right? They all have the same fractal dimension, so they're common in that sense, and that seems to be the thing that relates them. And so if I make the pattern more complex in terms of this n factor, this exponent seems to go down. And so obstacle distributions with no internal length scale appear to induce anomalous behavior. So this is to me, this is a really nice experiment because it really made concrete to me people can say all these things in literature, but this to me was a really nice, clear example of how you can induce anomalous diffusion in a fairly simple macroscopic system. I mean, the system is bent scale system. And I should have mentioned that the simulation and this work have both been recently published in Water Resources Research. So, and the other thing that's important is there does seem to be some consistency, and this is a fit, you could argue, but I'm more interested in showing, and I've done a lot more experiments, and much numerical experiments, and much higher pattern number carpets. There does seem to be some consistency between the fractal dimension, the geometry, and the value that you would see in the exponent of n from those experiments. So I think that's quite helpful.
H is the Hurst?
H is the Hurst, yeah, or not the Hurst, it's the Haseldorff. Haseldorff, yeah. I think I have the equation up there, or maybe we went past at some point. Yeah, this is the definition of the fractal dimension. So there is a consistent connection between it, which is one of the other things I'm interested in. So now I've got time in the last 10 minutes. I want to think about, well, can we... So the whole idea about why that might be important is that normally when you have some kind of infiltration diffusion system and you put obstacles in there, you say, well, I'm still going to use the diffusion equation. I'm still going to try and use Darcy equation. I'm going to homogenize by changing the hydraulic conductivity and having a representative hydraulic conductivity. The whole point about those fractal patterns is you can't do that. You can't find a hydraulic conductivity that will give you the right result because that doesn't change the exponent. It just changes the rate at which it goes. It changes the coefficient but not the exponent. So now I want to say, well, how do you build a homogenized model? So I want to take these patterns and just assume they're kind of smeared out, and I go back to my one-dimensional problem again. And I'm saying, okay, I can, let's see how far I can get using fractional calculus. And what people do when they approach, so here's the same Stefan type problem I had before. I have the equation in the domain and the equation at the front, and the only thing I've done, and this is what people do when they start playing around with fractional derivatives, and what I did when I started playing around with fractional derivatives, you just say, well, I'll take the regular equation and just replace one of the terms of a fractional equivalent. And that's all I've done here. So I've just decided I'll go fractional in time because I know that's going to give me the sub-diffusive behavior. The only place the time appears is in this boundary condition. And it turns out that this is actually a very, in the fractional diffusion case, it's a very easy problem to solve analytically. I don't want to bore you with how you go through it. You just have to be a whiz at doing the Laplace transforms it's very straightforward to solve. And what's nice about this model is, if I was to solve this equation, I end up then with this S, which is now tracking the front, and I get this T over alpha upon 2 coming out. So if I choose alpha between 0 and 1, which is the restriction, then so this is actually, so this suggests to me, oh, this is good, this is a mimic. This model, from a phenomenological point of view, would recover the behavior that I'm seeing. So if I knew the Haseldorff component, the fractal dimension, I could calculate what the alpha was, and the homogenization would come by choosing the alpha and putting it into that equation. So it looks like so from a phenomenological point of view, that the fractional calculus delivers the goods. I'm able to model this system. I still maybe have to identify some appropriate conductivity to use, which obviously has a strange dimension, but I can do it. So, and again, you can see that. So I'm just trying to track what it would look like if I did it in log-log space. So I'd have this, plot this out as it looks like in the log-log plot. So what I want to do, and the same as alpha upon 2. So okay, so now let's see if I can do this numerically, because that's an analytical solution that I developed. Let me try and do it numerically. So let's go back to my numerical case. And I already know this diffuse interface model. I already know both by demonstration and by rigorous theory, if I wanted to do it, that in the converged limit where I let that epsilon go to 0, that my diffuse interface model will become the same as the sharp interface model. So I've got a lot of confidence, things seem to work. Let's go back and model this process using numerically with my diffuse interface model. And now what happens is, in the diffuse interface model, I put my fractional component into here. And it's a little tricky to solve numerically. What you have to do is you have to use these Grunwald weight approximations for that fractional derivative. So this fractional derivative now takes this form, if you wanted this thing of a standard discretization. And really all you're looking at is, this is very clear what this is, because it's just the sum. I mean, it's the finite difference approximation of df by dt summed back through time. So each of these sum elements would be f now minus f old divided by delta t, but you just do that back through time. And this k, this Grunwald weights, which is associated with that convolution integral I showed at the beginning of the talk, just as some kind of power law to k, as a function of alpha. If alpha is close to 1, k1 is 1, and all the other k's are small, and as alpha gets smaller and smaller, all the k's become more uniform. And I can think about this jtim minus p is just p time steps back in the past. So this is where the memory is coming in. And the right-hand side, I just use a standard. So I'm looking at an implicit finite difference scheme here, because it's all done at the current time step. And the way I would solve this numerically is I would just snag out from here the current f and put it on the left-hand side, and everything else gets put onto the right-hand side. It's a little tricky to do, but not that difficult. So this is what a molecule would look like. So if I'm solving that particular equation at this point, this is the space, which is given by this, and then this is going back through time, and this diminishing size of the circle is trying to indicate that the weight, the contribution of this point, diminishes back in time. And this solution, when I did it, was really pleasing to me. It came out, great. I put in alpha at 0.7. Well, maybe it's 0.395, but so I was very excited when I did it, because it took an afternoon, I should be honest to say. And so that took one afternoon. What took a year and a half after that was what happened when I compared it. So it's great. It has the right exponent. That's really important, right? But now let's compare it with the sharp analytical solution. And it doesn't work. It's off by a little bit. It still has the right slope, but it's not agreeing. And when I went and looked at more general Stefan problems, where I do have some specific heat in the problem, it was off by even more when I compared the solutions. So and it took me a long time to try. Well, it took some time to try. I still haven't quite figured it out for the general Stefan problem. Here I can actually make some progress on this. In fact, there's no reason why, even though in the regular case, the diffuse interface model and the sharp interface model converge, which is a kind of central tenet of diffuse interface modeling. I mean, that you do a diffuse interface, it converges to the sharp model. I mean, it's well known, right? Well, here it doesn't look like that. That's not going to be the case. It's only when alpha becomes 1 that they will converge. And you can see that kind of fairly readily just by comparing the two equations I'm solving. So these are the two main kind of equations that I solve. And there's no way, because this now, you know, in the alpha equals 1 case, this is just a sharp change, basically, in the limit. But now it's not a sharp change. It's actually spread out through space. So there's no way that the H that solves this equation can solve this one, because this is a positive, finite, distributed source term. So there's no way that my head field can solve the head field that solves the sharp equation, which is this linear head, 1 minus x upon s, can possibly be a solution of this equation, unless alpha equals 1. So they can't agree. Those two solutions can't agree. Unfortunately, for this particular problem, I was able to actually come up with an analytical solution for this case. And I can show that more formally. So when I take the actual solution for this problem, it's not so bad. Well, it's pretty good, right? So I can find an closed form solution for this problem, which agrees with my numerical solution. But it disagrees with the closed form solution of the sharp interface. So the diffuse interface model and sharp interface model are different in that particular case. But the key question here is, and this is still, you know, one that hangs over, is, but what is the correct physical model of those? So the trouble is, I have these, so phenomenologically I can take a sharp interface model, I can take a diffuse interface model, and I can reproduce anomalous diffusion for this fairly simple infiltration system, but I have no idea which one, even though they give me the same exponent, which is good, and maybe I'm being fussy about the coefficient, but it's just to me fascinating that it's not just a simple case then of replacing the derivatives, the integer derivatives of fractional derivatives to get to the answer that you want. And so, in conclusion, I think I did pretty well. So we talk about anomalous diffusion as where the length scale associated with the diffusion doesn't scale as time t to the half. Sub-diffusion, which is the one I've looked at mostly here, is the case where it's less than 1/2. I've shown that you can, a simple system involving infiltration can induce this behavior, and you can see a very clear signal, unambiguous signal of anomalous diffusion by doing this simple experiments where we can reduce it, you know, from 0.5 down to 0.3, provided that the pattern to which we're infiltrating doesn't have any recognizable internal length scale. And maybe we can, in this particular case of these fractals, we can show that there is some reasonable relationship or, you know, consistency between the fractal dimension and what we might get for n. It would be nice if it had been a simpler thing. I'm working with someone in Brazil to come up with something which might actually be more definitive connection. And we can develop homogenized models that will reproduce this behavior from a nomological point of view, but we have a diffuse model and a sharp model, and the problem is that when alpha is non-integer, we don't know which one of those is physically valid. So hopefully I've given some idea of the kind of things that have been going on in my small group related to anomalous diffusion. I'm going to call it quits there and take any questions.
Thank you very much, Vaughan. We have time for questions.
Thank you, Vaughan. As always, I always enjoy your seminar. So
they're always a good laugh, aren't they?
No. It's really neat. I'm not convinced by your explanation about the length scale and the fact that when you have a regular pattern, that the fact that you. So the argument is as follows: that you have a length. Indeed, you have a length scale, but you have also a diffusivity coefficient. So that brings a time scale. So what I would argue is that the large time asymptotics should be square root of time, because you have time which is large. You don't see that length scale at large time. So I don't think that the argument that you have is based on this fractality,
Okay.
of course, but it's not based on the length scale. And actually, your numerical experiments show that you have basically a square root when you have this regular pattern.
Yeah, when you have the regular pattern, you have a square root.
Yes.
Yeah.
Yes, but that has nothing to do with the length scale, because it's a large time asymptotics. The large asymptotics is a similarity solution.
Okay, because of the fact you just look as you just go around each. I mean, so in general, you know, at the small scales, you wouldn't see the square root as being averaged out over.
Exactly.
Yeah, so you're right. Yeah. So if I looked at just the first thing, then I would see the. Yeah. So I'm only arguing that the overall behavior in that pattern, you know, once you have enough repeats of the pattern, it quickly reestablishes back to the normal diffusion case.
Exactly.
Yeah. So I mean, if I was just to take two. You know, a tube with just two fractal carpets. By the time I got to by the time I matched it, it would look like the square root of the time. Right, it goes back to that. But so once your largest, so in other words, in any system, once the heterogeneity length scale becomes even a slight bit less, 50%, but maybe not even that much less than the total length scale, then you don't see any anomalous behavior anymore. Yes. That's the point you're making.
Yes,
yes.
Yeah.
And that is the case, yeah.
And there's another comment I just want to make about when you look at induced seismicity and you look at the region of induced seismicity caused by injection of water, of fluid in general, in the field, I mean, it is striking that you see a square root of time. And that's kind of a large scale. And that's another experiment.
Well, but it would be, but I mean, the thing is, and so in answer to that question about the, so the idea, the one reason why these ideas have really taken a lot up in transport of porous media is because the heterogeneity in many systems of which you're looking at transport really does scale at very large scales. So you do see it appearing over large scales in that case. Because each time you go to a bigger scale, there's always some other bigger heterogeneity that's coming into the system. So I think that's a point I should have made there too, is that the length scale of the pattern is the dimension. But once the length scale of the pattern becomes smaller than the dimension, then by the argument that you make, it's going to go back to t to the half. Yeah. Good point.
If you look at this as a perturbation problem, right? When your alpha is close to 1 but not quite, then if you expand your operator, you should end up with a pure differential operator. I'm guessing a fourth order system. That expansion should also correspond to the correction of the large time asymptotics.
Okay.
So in that region, you should end up with a constant coefficient PD that approximates the fractional differential equation with, again, at a time that are large but finite.
That's a very interesting idea.
Do you know anything?
No, I don't, but it's something that I could...
Because in the waste community, there is something related to the low frequency expansion, which is...
Okay, yeah. So you're saying just assume that alpha is close to 1 and then just do a classic linear perturbation analysis about that.
Or time is large but finite.
Yeah. That's an interesting idea.
Maybe last question, because we have Geo-Engineering following.
So I have a question about the analytical solution in case of the fractional exponent. Fractional differential equations. Can you please go one slide back? Yeah. So here, in deriving the analytical solution,
for this problem here?
Yeah, for this problem. Did you choose some specific epsilon?
No, I didn't. The way, so this particular model I have is really based on what I would call an enthalpy model for phase change. It was a very classic model. And it's not really a classic, it is a diffuse interface model in my mind, but it's not a classic diffuse interface model because rather than having defining the diffuse interface over space, it defines it over the variable, over the temperature or over the pressure in this case. And the 39 years experience I have, one of the main things I was able to do in that 39 years was to actually develop a solution for that diffuse interface model where it was to basically 0. So there was no, I don't have to convert it. So the parameter epsilon doesn't enter into the solution. So I'm able to do it, as a sharp thing, but it still is but it still has the concept of a diffuse interface model, but I can solve it right at the converged point, if that makes sense.
So what I was really wondering about and why I asked this question is, like when we solve this equation numerically,
Yeah.
If we try to, like if you have more and more grid points and reduce the epsilon,
No.
is it in?
No, it wouldn't. That set doesn't come into point because epsilon is, in this particular model, the epsilon is implicit. It's not an actual physical space value.
Okay.
It's actually I mean, I can show you afterwards,
Yeah,
but
it's not defined in terms of grid.
It's not like a classical phase field model where it would be over a given. So there's not a number of grid points.
Okay,
In fact, there's just always just one grid point. But there isn't any. I mean, the solution is. I mean, as you saw. In the integer case, the solution is very accurate and reliable. So it would have very few node points. If I increase the number of node points in this problem, I would get exactly the same answer.
Okay.
Yeah, it's good conversion at that point. That's a good question.
Unfortunately, we have to finish because there's another seminar right after
In here as
Vaughan.
well.
But Vaughan is around, and you're welcome to ask him questions. Thank you.